In this section, we'll be looking at a couple more advanced problems involving friction. Let's look at this first example. In this case, George is attempting to pull a sled that is initially at rest. He pulls on a rope that's attached to the sled, as mentioned here, and it gives us both the coefficient of static friction and the coefficient of kinetic friction. And so in part A, he's going to be pulling with a force of 100 newtons on the sled. And what we're being asked to find is the frictional force as well as the acceleration of the sled. Well, let's start like we always do by drawing a picture. Here's the sled. Here's the child sitting on top of it. I put the masses here so I don't forget. I draw the rope, George, and I also indicate the angle so that I have it here. I now choose my origin in positive direction. I'll put the origin to be where the sled is originally located, and my positive x is to the right, and my positive y is upwards. I'll now draw a free body diagram for the sled. In this case, gravity acts downwards, and it has a force of 490 newtons because the total mass of the object is 50 kilograms, the 5 kilograms of the sled plus the 45 kilogram child. The normal force is pointing upwards, but in this case we need to be careful. It doesn't exactly balance out gravity because the force of tension has a vertical component. I draw the force of tension, and then I draw my frictional force backwards. You'll notice that I didn't put F sub k or F sub s down yet because I don't actually know if the sled's going to move. I don't know if the force that George is pulling with will be enough that will allow the sled to get moving. And that's going to be an important point I'm going to have to look at later. And let's go ahead and start writing down in part A, Newton's second law. I'll need to write this down in both the x and the y direction. And so in the x direction, I have the x component of tension acting in the positive x direction and friction acting in the negative direction, and this is going to be equal to 50A. I start plugging in information, and I know that the force of tension is 100 and that the angle is 40 degrees and that angle is adjacent to the horizontal, so it's cosine of 40 degrees to find the component. That gives me the force of tension in the x direction, and with friction here, you can see that's equal to 50A. Now again, I don't know whether it's static or kinetic friction, so really I can't go any further here. And so I'll have to start looking in the y direction for some more information. In the y direction, I have the normal force acting upwards, the force of tension in the y direction acting upwards, and gravity acting downwards in the negative direction. The sled's not going to move up or down, and so the acceleration in the y direction is 0. Now you might ask yourself, it is possible that the force of tension in the rope, because it has a vertical component, could cause the sled to lift off the ground, but I think it's pretty clear that a 100 Newton force can never cause a sled to lift up when gravity has a force of 490 newtons. There's no way the component could be bigger than the hypotenuse, and the hypotenuse is much less than the force of gravity. So let's start filling in information that we know. The force of tension in the y direction is given by 100 times sine 40. We plug in gravity, and that allows us to calculate the normal force. And so at this point, I can start calculating the force of kinetic friction and the maximum static friction force. And I'm first going to look at the maximum static friction force because I need to know the answer, does the sled move? And that's going to be important because it's going to let me know, is the sled actually sliding or is the sled attempting to slide? That information has not been given to me just yet. And so let's calculate the maximum static friction force. I know the coefficient and I know the normal force, so I can plug those in, and I find that the maximum static friction force is 85.1 newtons. And so if we go back to our Newton's second law in the x direction, what you'll notice is that the force of tension in the x direction is 76.6 newtons. Since the force of tension in the x direction is less than the maximum static friction force, we know the object's not going to move. And so the force of friction in this case is static friction, and static friction is always calculated by balancing out the applied force. In this case, that applied force is force of tension in the x direction, 76.6 newtons, and so that tells us the object doesn't move, and the acceleration equals 0 meters per second squared. You should be careful here, and I put this in a note, that the kinetic friction force, if we calculate it, is 63.9 newtons. And so in this case, our force of tension in the x direction would be big enough to overcome this kinetic friction force, but that's not what's relevant. That would assume the sled was already sliding. And so if the sled was already sliding and we were able to apply a force of tension of 100 newtons, then yes, the object would accelerate to the right. But the object was not moving to begin with, so in this case, we needed to get it started, and we've discussed this multiple times before. It often takes more force to get it started, and then once it gets started moving, you can apply less force. In this case, the amount of force that we were applying would have been enough to keep it going once it was already moving, but it was not enough to get it started. In part B, the force is 140 newtons, and so let's see if this changes the situation. We do the same thing as before. We write down Newton's second law in the x direction, plug in our values, find the components, and in this case we see that the force of tension in the x direction has increased to 107.2. This makes us pretty confident that it's going to start moving. But let's keep going just to check. In our y direction, we write down the same information as before. And in this case, we can see that the normal force goes down. Now it's only 400 newtons, and that's because we're applying more upwards force from our tension than we were before. And so we ask the question, does the sled move? And we calculate that F sub S max is only 80 newtons. Now, since the force of tension in the x direction is bigger than F sub S max, that's to say the 107.2 is bigger than the 80 newtons, then the sled will move. This means that now we know our force of friction is going to be kinetic friction. The sled's going to slide. And so we can plug that information into our x direction, and now we start to solve the information, and in this case we calculate the force of kinetic friction by using its coefficient, and that tells us that the acceleration is 0.95 meters per second squared. So that example exposed you to using both the static friction formula and the kinetic friction formula in a problem where you're not told whether the object's moving or not. In this example, we know that the block's initially sliding, so we know we're going to be using kinetic friction. Now, this problem is going to be quite complex, and so make sure to take your time working through it, and if you do understand this problem, then you're well on your way to really understanding how to apply Newton's laws to get your kinematics and to use them in a situation involving friction. We don't have to draw a picture here because the picture is already given to us, but so let's start by drawing our origin in positive direction. When we first look, the block is already sliding. It's moving at 3.5 meters per second up the ramp. We'll go ahead and put our origin where it's originally located, and as we've done with our ramp problem before, we let the x-axis point up the ramp and the y-axis point perpendicular to the ramp. We'll now go ahead and draw a free body diagram. In this case, we have gravity pointing downwards, and because the block has a mass of 2 kilograms, that force is 19.6 newtons. The normal force is always perpendicular to the surface. Remember, a normal force is a perpendicular force, so it points perpendicular to the surface, and the force of kinetic friction points down the ramp. Again, remember when we first started looking at it, the block was already sliding, and so there is no force up the ramp. Again, if there's nothing touching it, there's nothing acting. And yes, there was some force originally that had to get it moving, but we no longer see that force, so the block is really in the process of slowing down, and it's, quote, it's inertia that's causing it to keep moving. There is no force up the ramp. Let's go ahead and start writing down Newton's second law in the x direction. In this case, we actually have two forces pointing down the ramp. The negative force of friction, but also there's a component of gravity that points in the x direction as well. And this is going to lead to a negative acceleration, so I put a negative sign here so my A becomes positive. We know how to calculate the force of kinetic friction, and that depends on the coefficient which is given to us and the normal force which we'll need to find. Now we also need to find the component of gravity. And so because it's a little bit tricky to calculate the force of gravity on a ramp, I'll go ahead and draw my free body diagram, even though that's not something you should typically do, so we can see things a little more clearly. In this case, you can see the angle in blue, and what we see is I drew some angles on the free body diagram. And so because the angle that is adjacent to the x-axis is 70 degrees, then I know that the force of gravity is 19.6 times cosine 70 degrees. I can go ahead and plug in the information I have and simplify, and that really gets me as far as I can go. I can't find the acceleration without knowing the normal force, and I'll need to use Newton's second law in the y direction to calculate that. So let's write down F net equals ma in the y direction. In this case, our normal force is positive, and we have a y component of gravity. The acceleration is 0 because the block's not crashing through the ramp, and it's not jumping off the ramp. And so we now need to find the force of gravity in the y direction, but as you can see by my picture, that the angle that is adjacent to the y-axis is 20 degrees, and so I know that this is 19.6 times cosine 20 degrees. And that tells me then that the normal force is 18.4 newtons. Now, just to remind you about the components here, we found both the x component and the y component of gravity, and in purple I drew it here so that you can see the y component is 18.4, the x component is 6.7, and if I draw that all on a triangle, then the hypotenuse is 19.6, which is the force of gravity on a 2 kilogram block. And now that I've written all that information down, I can solve for my acceleration in the x direction, and I do that by plugging in this normal force and solving and finding that the acceleration is 4.7 meters per second squared. That allows me to finally write down my kinematic variables in the x direction. And the acceleration is negative 4.7. And that's because the acceleration is down the ramp, and that's in the negative direction. The initial velocity is up the ramp, and that's positive 3.5, and I chose my initial position to be at the origin. In the y direction, again, there's no acceleration, there's no initial velocity, and the initial position is 0. And that just shows that there's no motion in the y direction, as we said before. Now let's go ahead and start working with part A. And in part A, we need to ask our mathematical question, what is x when t equals 0.5 seconds? And so we start plugging in our information, the acceleration and the initial velocity that we just found, as well as the time. And that allows us to find that it is 1.2 meters farther along the ramp. And so it has traveled 1.2 meters up the ramp. In part B, we're trying to find the maximum height. And so this is our same question. When is the velocity 0? In this case, what we're really referring to is the x velocity. When has it stopped moving along the ramp? And so what is t when v sub x equals 0? We plug in our information, and this allows us to solve for the time. And in our case, the time is 0.74 seconds. And so it takes 0.74 seconds to come to a stop, which is to say, to reach its maximum height. And so in part C, it asks for what is this maximum height. Now, it's not really clear what they're asking for, whether it's along the ramp or vertically, but we're going to go ahead and find both just so that you can see. And so what is x when t equals 0.74 seconds? Let's first find out how far it is along the ramp when it comes to a stop. We use our first kinematic equation, plug in our values, and we find that it's 1.3 meters along the ramp. A little bit of trigonometry allows us to find the value for y in this situation, and so let's just assume that its max height is what they were asking for, how high it is above the table, and in this case, it's 0.44 meters above the table. To do the next part, it's asking us for information about the block on its way down. In this case, we're going to have to redraw our free body diagram, because if the block continues to slide back down the ramp, then the force of friction is going to change direction. The force of friction is going to point up the ramp. And so we do that by drawing a new free body diagram that looks pretty much the same, except that friction points up the ramp in this situation. Now you might ask yourself, are we sure that the block's going to slide down? And that would require information about the coefficient of static friction. In this case, it turns out that as long as the coefficient of static friction is not too big, that the block really will slide back down the ramp. But this problem was already complicated enough, and so let me go ahead and ignore that right now and just know that the force of gravity is going to be enough to pull this object back down as long as the coefficient of static friction is, say, no bigger than 0.2 or 0.25 or something like that. We proceed the same way we always do. Now we need to write down Newton's second law, and in this case, the force of kinetic friction is in the positive direction, and so we can calculate our normal force by using the y direction. But again, our normal force hasn't changed. It's still 18.4 newtons. And so we can use that information and plug it in. And again, our force of gravity in the x direction also hasn't changed. It's still 6.7 in the negative direction. And so we can calculate our acceleration. It's now negative 1.95, which is less than it was before. And again, that makes sense because before we had both friction and gravity slowing it down on the way up, but on the way down, gravity is helping it move down the ramp, and friction is opposing its motion down the ramp. Now we can write down the kinematic variables. Its acceleration is negative 1.95 meters per second squared. Its initial velocity is 0. And its initial position is 1.3 meters because at max height is 1.3 meters farther along the ramp. So now we can finally ask in part D, what is t when x equals 0, when it returns to its original position? We use the first kinematic equation and plug in the information we're given. This just requires us to solve for time. And we can see that it takes 1.15 seconds to return. In part E, we're being asked for its velocity when it finally gets back to its original position. And now that we know the time, this is simply what is v when t equals 1.15 seconds. We plug in the information into the second kinematic equation, and we find that its speed is 2.2 meters per second. Now, it's worth remarking, when we did this problem before, there was a lot of symmetries in the problem. Because of friction, that symmetry is no longer there. As you can see here, it took 0.74 seconds to reach its maximum height, but it took 1.15 seconds to return. So those times are no longer equal. You can also see that it was sent up with a velocity of 3.5 meters per second, and if there was no friction, it would have that same speed when it returned. But in this case, because of friction, its speed is less, it's only 2.2 meters per second. So as I said, you should feel good if you understand this problem. If not, you should take the time to work through it carefully. This is a good example of using friction, as well as trying to understand kinematics and forces in a problem in 2 dimensions, in this case, a block on a ramp.